Okay, so yeah, my title here is Massive Black. That's what I was told to talk about. So I thought, okay, I'll build a whole talk around whatever title Greg gave me. So you want to know that? That's the name of our simulation suite, and we didn't really pick it with marketing in mind. Basically, we had like 2 seconds before a talk to think of something, and it was so we saw supermassive black hole written on a slide, so we picked the middle 2 words. It could have been super hole instead. Maybe that's. I don't know. Okay. I mean,
you can always change it.
Okay. For the next set. Okay, so these things are more important than you might think. I guess that, you know, millennium, illustrious, all these things, I guess they put a lot of thought into it, and we didn't. So. Okay, so one thing I like to show you is the data from the simulation is public, and many people have downloaded it, but if you haven't seen it, it's also fun to kind of play. We have a browser that will, well, it's loaded up 3 times, but anyway, it's, so basically with any web browser, you can have a look at, this is the Massive Black 2 simulation, which is an SPH simulation. I'll come back to what it is in a second. But you can click on data access, and there's some user agreement. I'm not sure why we need that for legal reasons. It's an American thing, I guess, or something. But anyway, and what you can do here, you can browse through the simulation visually. Just, for example, you can change different snapshots. That's an early universe snapshot. This is later universe. I guess you can't see it very well. You can zoom in, and we go down to 1 kiloparsec pixels, so you can zoom in and pan around and look at things. You can jump to different, say, friends of friends groups, and it gives you statistics about them. You can zoom in and have a look. For example, you want to look at this galaxy here. It tells you that it's probably a ridiculous one. It has a mass of 6 times 10 to the 14 solar masses. Okay, I'm not going to hide things from you, so this is obviously crazy. But anyway, star formation rate 400 solar masses per year. Anyway,
so for a $5 donation, you get to name any one of these.
Exactly. Yeah, sure. We can also subgrid put your face in there if you want. Okay, so you can do things like you can also you can zoom in, you know, obviously quite far. Into, and you can see it's in a sea of very hot gas. This is at redshift 0. It's the most massive object in there, the most massive cluster. So it's in a sea of very hot gas. And you can change layers. You can look at the stars, for example. And that's what the stars look like. I guess I can see things on my computer. You can't, but okay. So anyway, this is something you can play around with and download the data. All the data is public, and you can have a look and explore. And I'll show you some funny things that I found later, just panning around in this space. Okay, so what am I going to talk about? Basically, I was going to talk about AGN and supermassive black holes at high and low redshift. I'll start off with talking more about high redshift things. So one thing we'd like to know is, where do supermassive black holes form? At very high redshifts, they're very rare. We'd like to have a very big volume to look for them. So we'd like a simulation to be, say, a gigaparsec in size. Usually people do a zoom approach because they want to maximize their resolution and minimize computer time. So you might pick from this big volume. Usually people don't use a gigaparsec. Things like 100 or 50 megaparsecs are common. But you would select some galaxy based on your hope that there'll be a nice quasar forming there, and then resimulate. Often what you would actually do, because nobody ever resimulates, at least so far from hydro simulations, is pick a dark matter halo and hope there's going to be a quasar there. Then you do a zoom simulation, and you find you've got, maybe, if you're lucky, some nice galaxy. There, of course, would be a whole bunch of other galaxies. Who knows what they're doing? Makes it difficult to do statistics. You could do, as Romain just showed, 50 zoom runs, and basically 50 zoom runs, in the end you're approximating what we're trying to do brute force, basically by doing a large uniform volume, so that that's the same kind of idea. So you might have all these other galaxies here, and you don't know whether they've got black holes in or not. You might know this one, whether it had the right combination of large-scale gas inflows to form a supermassive black hole. And this applies not only to quasars at high redshift, but obviously also to galaxies forming in halos at low redshift. So our brute force solution to that is to run a uniform volume gigaparsec simulation. This is a massive black 1 simulation. This is from, I guess things have been cut off, so anyway, this is from 2012, and the idea is it has a kiloparsec resolution, and
Great simulations have diffraction spikes too. I love it.
Yeah, that's right. Yeah, you know, that's numerical effects. Okay, so why do we want to run such a huge thing? Well, if you have a statistical sample here, this is actually from the massive black 2 simulation, so there aren't any very massive black holes in there, but it's a bit smaller volume. I'll come to that in a second. But anyway, here is the halo mass. Say you pick a halo mass of 10 to the 12. What kind of black hole mass can you get in there? Well, at redshift 4, you have black holes of 10 to the 9, or sometimes even 10 to the 6, a whole bunch of 10 to the 6. So the large-scale environment can cause the black hole in the center to vary by a factor of 1,000.
Can you say one more time how you decide in your simulations how big the black hole is?
So you seed it with, when the halo forms, the minimum mass resolution for a halo, you seed it with the black hole in the center. You pick a seed mass, in this case it's 10 to the 5, but I'll show later on we tried 10 to the 3 and 10 to the 4, and I'm sure Joop has probably tried 100 million other ones and before me. But anyway, we've shown that it doesn't actually matter, the seed mass. Okay. So here's the AGN luminosity. Again, you get this huge spread. So remember that these are dark matter halos. If you had a zoom run, you might pick one of these and say, okay, I really think this black hole I'm interested in is going to form there. But of course, you're missing out on all the other things. And so it's nice to be able to have that possibility. Okay, so here's an example. Here are these two, say here's a low mass, low luminosity quasar in a 10 to the 12 solar mass halo, and this is the large scale environment around a high luminosity, high mass one. And you can see the large scale environment is different. Somehow that environment has enabled more gas to flow in to the center of the black hole here. And so I say large scales because it seems to be that obviously we do best at resolving physics on large scales in the simulation. That's what we really care about the most. We're looking at cosmology, large-scale gas inflows that flow in from, say, several megaparsecs all the way into the black hole. And so that's physics that we're able to capture in our cosmological framework where the initial conditions are well specified. It's cosmology, right? So that's what we can do best, and that's why we concentrate on that.
So Rupert, does that scatter maintain until redshift 0, or at least lower redshift, or does it get completely... because that would be hard to believe that you have anything close to
I'll show you
sigma relation.
Yeah, I'll show you the M sigma relation later. So it does not. It has tightened up. Okay. So here's the simulation, just to get technical on you slightly. So Nishi Kandai ran the first two, and Yufeng here is heroically running the last one. So the last one is running on this computer called Blue Waters NCSA. It's running on the full machine, so that's about 0.7 million cores, and so he totally rewrote the code so it can handle nearly 1 trillion SPH particles, and it has a mass resolution of order 10 to the 6 solar masses in a 400 megaparsec volume. And so I put question mark for how far it's actually running, because to run to redshift 0, it would need more than 1 billion CPU hours, and that's too much. So we'll see where it gets to. Hopefully it will get to at least redshift of, say, 5 or 6. So there's, these things are difficult to do. So this one here got to redshift 0. It's a smaller box, but it does have this mass resolution 10 to the 6, which is decent. So, for example, what can you do with that? Well, here's simulation mass versus year, and we're down to 100 particles, say, could resolve a dwarf galaxy, say, if we had that mass resolution. So that's kind of the thing that we can say we can resolve. Say, look at the crude statistics like the galaxy stellar mass function for those things. But in this talk, because we're talking about AGN feedback, we're more interested in the more massive things. Okay, so the physics that went in. So people have talked a little bit about physics. Old SPH or repo has been mentioned, things like that. So these two were run with so-called old physics, so that the entropy conserving formulation from 2002, Spindle and Hernquist, a star formation model from 2003, and a uniform UV background from 1996. So this is old physics. So what we're going to see is I'm going to talk about results from this in this talk, because this one here, we put in Phil Hodgkin's pressure entropy SPH, molecular hydrogen model, and a non-uniform UV background, but this thing is, as I said, it's still running, so I don't have any results for that. These are the only results I have. These are actual pictures from it. That's all I could get from it. But it's running right now at this very moment. And so what I'm going to talk about is old SPH. So what can old SPH do? So this is kind of fun because people may sort of discard out of hand, this is old stuff from a long time ago, it must be really bad. But do we really improve things so much if we put in all this other fancy stuff? So I'll show you what these two simulations run with so-called OSPH can do. So for the very high redshift quasars, these are results from a few years ago, and we find that you can get growth of supermassive black holes so that they reach 10 to the 9 and so on when you want them to. And this basically is because they are gas inflows that actually enable the black holes to reach Eddington pretty easily in these very high density rare regions. Remember, you've got a gigaparsec volume, and in those very rare regions where you do form a handful of 10 to the 9 solar mass black holes in that gigaparsec by that redshift, all that's going on is cosmology tells you the initial conditions, tells you gravity, forces gas in, and then you can reach Eddington. And so it doesn't really matter what your black hole model is, as long as you allow that the gas, you actually weigh super Eddington in terms of the amount of gas that reaches the black hole. So it's actually, the supply of gas enables these things to grow. Okay? And then at some point, you reach the point where you have feedback from the black hole. It's got big enough that it actually slows down the inflow and then quenches the
I mean, gas supply is very rarely the limiting factor of actual accretion. It's usually angular momentum that's the... So
sure.
What kind of resolution, what area are you resolving to say the gas actually flows into that area? And then we can kind of imagine what happens within that area.
Sure, so we have kiloparsec resolution, so that's...
Okay,
that's
so gas reaches a kiloparsec.
Sure, there's an enormous amount of gas that reaches a kiloparsec that would enable very super Eddington accretion, and then we make the assumption that actually that is able to reach Eddington. We do cut it off at Eddington. But, so yeah, you could say if somehow that gas with all that that inflow doesn't actually reach the black hole, then you would have problems. Okay, so
this is really kind of a charting of gas flow into the central kiloparsec.
Yeah,
and
yeah,
then
that's
you
right.
have this model that...
Yeah, that's right. So basically, that's what we know how to do. You know, so in the cosmological simulation, obviously we can't look at very small scales, but as far as we're concerned, another half of the picture, and maybe the more important one, is actually where that gas comes from, and that's what we can do. So that we're focused on that. Okay, so what we can do a little bit is we can do some tests, limited resolution tests, because now we know where the black holes form. We can zoom in to those black holes using these zoom methods, and we pick them, the target objects from a hydro simulation. So people don't normally do that, but here we can do it. We know, because they don't normally have the full hydro over the uniform volume, but we can do it, and we can do some things. Obviously our resolution is, we're not going to increase it very much because we're not doing this adaptive mesh stuff, but here we can change the mass resolution by a factor of about 100, and we find that although the accretion is different in the initial stages, not surprisingly, the final black hole mass is pretty similar, and here just 3 zoom halos, and so we're pretty insensitive to the resolution in terms of what these supermassive, remember these at redshifts of say 5 and 6 reach. We could try different feedback deposition schemes. We could try putting in a constant volume, so all gas particles within a certain radius. We tried a few radii, 1, 2, 3, 5 kiloparsecs, or constant mass, constant Lagrangian, so we go out to a certain number of particles, depositing these thermal bombs that Romain was talking about. It doesn't actually appear to affect the final black hole mass very much, in terms of that. It certainly doesn't prevent them reaching that mass, but of course this is a very limited change in the feedback prescription, but at least it shows that constant volume or constant mass doesn't affect things. You could try the seed mass, so you could try varying that by a factor of say 100 here from 10 to the 3, 10 to the 4, 10 to the 5, and we do find that the final black hole mass is all pretty similar, it's just one halo, but the lower mass C does grow later, and then it grows faster and catches up and then quenches. It's kind of interesting, but the bottom line is we do form 10 to the 9 solar mass black holes at redshift 6, even with a smaller seed like that. And then one thing that does cause some differences is changing the formulation of SPH to Phil Hopkins' pressure entropy SPH, and that does give you bigger. The growth is broadly similar in the way it happens. You have this Eddington limited accretion of a couple of gigayear or so, but you do get bigger black hole masses, and so that's something that maybe remember there is this one free parameter in terms of the amount of feedback that is energy that is emitted, and that could be adjusted maybe, but that's something that is slightly different.
What is your accretion efficiency?
So the accretion, I think is 0.1.
And then you, when
Minus
you treat
5%.
gas, you remove the amount of gas that has been radiated away, right?
Yeah.
You correct for that. And you can still grow 10 to the 6, 10 to the 9 mass black hole from a stellar mass C.
I mean, we have low resolution, right? So this is the smallest we try. But yeah, the initial stages would have to be some other high resolution thing, which people are trying. Okay, so Ramses, okay, this is Johan Dubois took the initial conditions from our SPH run and then did a zoom with Ramses, and it's sort of broadly similar. This, it stopped a bit earlier, but it doesn't stop. Having much higher resolution doesn't stop it working. There are obviously big differences in detail, so it depends what question you're asking. But, okay.
Rupert?
Yeah. Okay, so high rate shifts, we're concentrating on large scale gas inflows. As far as we can tell, given that it seems to work to form these supermassive black holes at high rate shift, the black hole subgrid modeling isn't that important. You can compare to observations. Quasi-luminosity function, okay, maybe we're too steep in the slope, but it's not too bad. The galaxy stellar mass functions at different redshifts. Turns out that with all these observational comparisons, there are always issues that come in which are at least as big as, well, maybe not at least as big, but similar size to what the simulation uncertainties might be. So one of these, when comparing galaxy stellar mass functions, is that when people compare they use a UV luminosity and an assumed mass to light ratio relation, which is this line here, to then apply to the observations. It turns out you can measure what the relation is in simulations as a function of redshift, and it actually doesn't stay fixed, and it has a different slope. It's very flat. And so it turns out that this changes where the points would be. And so this is an uncertainty. You can get a factor of 10 difference in there.
Well, but we have to compare the luminosity functions directly. Why do you need mass functions?
Sure, because, okay, in the simulations, luminosity functions are a lot more difficult to compute. Right?
Star formation rate is just approximation of what they measure. What was that?
So you look at stuff.
Sure, okay, yeah, I mean, you can choose to compare, you know, there are uncertainties on both sides, so yeah, sure. I mean, you'd like to think in a simulation that the stellar mass is something you know best, right? So if you're a simulator, you can try and do that. But yeah, I agree that, you know, you would really like to compare basically both things. Okay, so at low redshift, we go from... Sorry?
Do you look into clustering?
Yeah, I do. Yeah, I don't have time to talk about it, unfortunately. In the paper we have it. That's actually the bit that I did, which I'm not talking about for some reason. So, okay, so anyway, so at low redshifts, we go to feedback limited. Phil Hopkins and authors showed that in terms of star formation, feedback is the most important thing that regulates star formation. And we expect, or we hope, that black hole accretion, for example, what is the scaling between the accretion rate and the local properties of the gas, is not governed by, say, that we use Bondi or anything else. It's governed by feedback. So feedback is telling you how much accretion there is given what local gas properties there are. So we'll look at low redshifts. Okay, I'll just move quickly in the last couple of minutes to low redshift. So massive black 2, this was a smaller box that ran to redshift 0, and the competition here is this illustrious simulation. And here's I was reading the BBC website one day and I saw this and I thought, wow, that's a pretty cool headline. So okay, so basically we're not as ambitious as them, I guess. I'm telling you that our massive black 2 simulation is based on SPH from 2002. So just how bad is it? Do we have a hope of recreating our universe in the lab or not? Are you sitting in our universe? Well, here's a slice through that massive black 2 simulation at redshift 0, and you can look and find galaxies. And so these are galaxies that you can see in there, made with old SPH, old star formation, and so on, right? Which supposedly old SPH can't form disks, and they're ugly electrical blobs most of the time. There seem to be some. One of the secrets might be that we have a large volume, and so basically we got
H2 regions or Kaufman blobs that we're looking at?
Sorry, what?
Are those H2 regions or Kaufman blobs that we're looking at?
I mean, these
These
are
are just stars, right?
this is a star map, and it's made in mapping
Blue stuff.
Sloan bands to RGB, and it's super saturated because the first version you couldn't see anything. So yeah, because it's a big volume, there are 10,000 Milky Way mass galaxies in there, so you can look at them. This is something I was looking through this yesterday while somebody was talking and I was not paying attention, but I was just looking for funny things to find, and I found all these donuts. Okay, there's not many donuts. I flipped through about 10,000 galaxies, and there were like these 10 donuts. So basically they're things where the AGN maybe has quenched star formation in the middle. But yeah, I don't know if these things are real or not. But I told you I would show everything, even if it looks like it's crap. So that's what these little donuts look like. Okay, so I'll just move on very quickly to one comparison. Okay, here's AGN luminosity function, which does okay, but there are still the discrepancies change with redshift. The simulation is this line, observations per day. So the discrepancies change with redshift. Some redshifts do better, higher redshifts, and then there's why is redshift 1 bad and redshift 0.5 good? I don't know. So one thing I want to do now, the last minute, is look at the galaxy stellar mass function. Here's the galaxy stellar mass function at redshift 0. There's some observations underneath. The simulation is mass vectors here. And here's earlier work by Oppenheimer, 2010, with no AGN feedback. We don't have a run with no AGN feedback, so I'm comparing to his. And you can see that this quenching by AGN does appear to reduce the number of high mass galaxies, the stellar masses. But it's very sensitive to many things. So for example, here you could say, let's cut out of our simulation sample all the AGN above certain luminosities, say 10 to the 41, 10 to the 43, 10 to the 45, okay. And it does change things. Also, this is basically our last point, is supposing we heard from Mariangela, for example, whether using Cirsic or Petrosian profiles affects things, and it does at this end, with huge differences. In the simulation, you can do various things to try and compute what is the stellar mass. You could take what we naively did in our papers. We just took all the gravitationally bound stellar mass in a subhalo and said that's the mass of the galaxy. But then you could do other things. You could just take the central galaxies, or you could take the centrals within two half-light radii of the center, and you get these things which are at least as big a difference as the quenching from AGN. Why did I put up these other criteria? It's because I was wanting to compare to Vogelsberg et al., the Arepa simulation, and here are the centrals only, which is that they plot. This is the centrals and so within two half-light radii. They don't have the gravitationally bound mass, right? So, if you plot our stuff on top of it, then here's our gravitationally bound mass. It's kind of like their centrals only. Their centrals only, our centrals only is down here. And so here's Mariangela's points, and here's earlier results. And so there's a huge, enormous uncertainty there. And with the AGN feedback, here's my summary. Selection and measurement of L star, just to pick one statistic, and I'm sure it applies to many. The galaxies in simulations and the observations can give you easily a mass function that changes as much as AGN feedback. So you really have to be careful. It's always nice to focus on the physics, it's more interesting, but there are many sneaky things that simulators and observers do, and that probably holds for a lot of things. Okay, so that's why at high Z, we can say we can grow black holes as large as observed within standard cosmology, assuming that this gas that gets to 1 kiloparsec and is cold and inflowing does reach the black hole. At low redshifts, we seem to be doing okay. Maybe the galaxy star mass function is too steep for these things, even with so-called old SPH, right? And so you have to wonder whether physical improvements in the simulations are, they have to go along hand with better interpretation and better matching of what is done in observations and simulations. I know it's kind of a boring standard point, but it really does make a difference for these things. And so going on with, why don't you measure the luminosity function? Sure, we should do that, right, instead of the galaxy stellar mass function. That would probably help. So, okay, that's it.
Thank you. Eric, so you stressed the role of AGN feedback for the lower redshifts. You didn't talk about it at high redshift. Is it
Sure.
simply that the feedback is there in the simulation, but it's not effective because the gas inflows are so dense?
No, it is effective. Otherwise, if it wasn't, the black holes would grow and grow and grow at Eddington. I mean, they do have enough infalling gas. I mean, there's still structure forming. It's just that it is cut off, not by starvation, but by the feedback. And so you can have a look and see. I'm not sure that do I have any. These are these filaments of inflowing gas that come in. Here's the virial radius, and eventually, at some point, there's hot gas that, as we've seen, builds up around it, and that does stop it. Okay.
Somewhere at the end of your talk, I think you showed the black hole mass halo mass relation.
Oh, I skipped through it, sorry, yeah.
Can you comment on that?
Sure, that's fine. Okay, here's M sigma, I guess. So
that's M sigma.
Yeah, so the simulation is this cloud with these black points, and then, where's the halo mass? Do I have the halo mass?
It's in the beginning of your talk.
Here it is. Right, here's the...
That's stellar mass.
Is that, oh, sorry.
In the beginning of one of your first slides showed some of that. You made a point that large-scale flows can change things.
But that was a high
thousand scattered.
Sorry.
For redshift 4.
Right.
Yeah, that was a redshift 4.
I was wondering if you have the same for redshift 0.
Yeah, unfortunately, no, I don't. I mean, I probably got it somewhere, but yeah, sorry.
But this kind of, I guess, is much smaller, right?
Yeah, it is.
So this slide that I just mentioned in the beginning, when you said large-scale inflows can change the black hole mass, a fixed halo mass, by orders of magnitude.
Yeah.
Now that surprised me because large-scale inflows follow the dark matter, so they should also change the dark. But you're talking about fixed dark matter halo mass.
Yeah, sure, yeah.
So do you understand why your black holes at fixed dark matter halo mass have such a huge scatter?
So, okay, to some extent, what you have to do is just go back and look and see what's going on. I don't have any...
Is it actually systematic? It's always in the same sense that those in the densest environments of fixed halo mass get the biggest black hole masses?
So, okay, anecdotally, just by looking at it, yes, but
you haven't shown us that that's actually the case, that it's a
No.
correlated environment. You just said
No.
there's a scatter.
Yeah, sure, exactly, right? So I'm assuming that it somehow is, but because that's basically what we can resolve as large-scale
Why
environment,
would
right?
the 1 kPC care more about the large-scale structure than the halo mass?
Yeah, sure.
That's impossible.
Yeah, I know.
I think it's, well,
Yeah,
it is
okay.
numerical, I think, and we would have the same. It's not that you're doing anything worse.
Okay, that's interesting, yeah, I don't know.
Just going back to that point, so there's an argument by Martin White that the clustering of quasars at redshift 4 is so strong that you can only tolerate 50% scatter in a relation between black hole, or between quasar luminosity and halo mass. Right, so anything that you do to increase the scatter, because the clustering is so strong at redshift 4, would only lower the clustering because you'd be putting quasars in lower mass halos. So I think if you look at the clustering, I think it has to be way underpredicted if you have that much scatter at redshift 4.
Assuming you know what halo mass the quasar should be
Well,
in.
the quasars have a bias of 14, so if you assume a duty cycle is the age of the universe, you barely have enough dark matter halos to put them in such that you can get a bias that high. So any scatter that you add only lowers the clustering.
If you would pick only the ones with a luminosity above 10 to the 11, then they are fairly narrow. Halo mass.
There needs to be less than 50% scatter in that relationship.
It needs to be.
Okay,
That's the claim.
so this...
For quasars above the
Number
luminosity.
observationally is
If you look at the most luminous ones, they have a very narrow range in halo mass.
It doesn't matter, there can't be that much
Okay,
scatter.
so
in the relationship.
this is 100 megaparsec box, right? And so there aren't really hardly any of those quasars in there. These are Sloan quasars, right?
Yeah, right.
So this is 100 megaparsec box. So
So
You know.
you're arguing that large-scale physics, which is Yope's point, right? Large-scale flows give rise to all the scatter, but then that has to then break down at the high luminosity end, otherwise you have a problem.
I mean, okay, you have to model the scatter and the cutoff carefully with enough volume, right? And so,
It can't be
I mean,
about
you can, you can,
the concentration parameter of zero. So maybe it depends on the concentration parameter inside 1 bin of halo mass.
yeah,
You
maybe.
can get a different black hole mass because the concentration is different.
Sure, okay. I mean, it would be nice to have a look and see, measure various statistics like that, large scale and small scale, and just see what, so that would be something fun to do, sure.
Can I perhaps now draw the discussion of Rupert's paper to close so that we have 20 minutes for discussion, but let's thank Rupert again.